MSM. So that's again a very modeling and simulation environment of multi-domain. So because I mentioned, right, it's not just electrical or mechanical, it's a wholesome thing. It's a complete amalgamation of all kinds of technologies. So these are some of the simulation software which try to mimic the actual automotive systems at hand. And you can simulate all kinds of things. Then you have the simulation X. That's again so the MSM used to be a French-based company. It has been taken over by Siemens, and this simulation is from ESI Logic. So it's again an introducing software for system solution. So these are again, why am I talking about these simulation software? Because they help us. They make a foundation for developing control strategies, or they help us for modeling. They help us in analyzing the performance, so that we can proceed towards more advanced we can proceed towards these things: improvement of performance, drivability, cost reductions. We can do all kinds of things, because directly we cannot just go to the vehicle and start tweaking the parameters, and then it's a very costly affair. It's sometimes it's dangerous for testing, but in simulation it is before going to the actual hardware, the field, we can always go back to the simulation part, right? And then we have DSpace also. So they have models for testing, and they also have hardware for hardware in loops or simulation testing. So then you have obviously the very friendly MathWorks, which is again very friendly not just to academics but to industry. So that they give us a platform, simulation platform, and then we can also develop control code, and also this support deployment of code into the microcontrollers and microprocessors or something, so that we can quickly test our control strategies. Then obviously Bosch gives a lot of electronic control units. We have fuel injectors, actuators, brakes, spark plugs, batteries, etc. So plenty of these are again they don't directly manufacture vehicles, but they indirectly support these the automotive industries. Then you have Cummins, which is quite specialized for engines and generators. And Eaton is also there. They mostly they're into heavy engineering. So mostly power design, manufacturing, sale of powertrain. So mostly heavy vehicles. They mostly deal with the controls and transmission. So yeah. So now so these were again the associated industries. It's not just, as I said, the jobs that they generate. It is also about the technologies, and since these industries may not be always expert in all of them, so they many times this provide subcomponents or subsystems. Many times they give the overall using this you can analyze the overall performance of the system, or towards it towards betterment or something. Okay. now now let us start now about the automotive system. So it's the first time that we look at it, automotive system is the motion, right? We are just interested in the motion of the vehicle. Initially, that's what it is expected to do. It's supposed to exhibit some speed, and the vehicle, a person who is inside the automotive the vehicle, you'll expect the vehicle to move. So that is an important thing. So now, having said that, we can always appreciate the fact that it's a speed versus time. Okay, so these are called drive cycles, or driving cycles. So there are a set of speed versus time. So you have some curves you might have seen. I don't know how many you might have seen. So they are characterized by something like this. Is not a very realistic drive cycle, but you have some speed versus time. So one might ask, so what is the big deal about that? So this actually it captures a lot of information. First thing is it tells about the so different places or different road condition, based on different conditions and different countries or different states, you will have different drive cycles. That actually characterizes the basic nature of the basic nature of the driving pattern of the driver, also the traffic conditions, also maybe the gradient of the vehicle. So plenty of attributes are involved here. Okay, so one thing you can also appreciate the fact that here there is acceleration, right? So you can see that in this situation you can have acceleration, and for a short time you can have constant speed, and then you can have deceleration, right? And then acceleration decreases. So this will tell you that what is the duration in which you are accelerating, so that the acceleration corresponds to how higher demand of torque. Similar to deceleration. So if there is deceleration, there'll be extra braking effort, and there'll be braking effort, and then there'll be There can be chances of doing regenerative braking also, right? So, and then obviously the area under the curve is nothing but the distance that is traveled. So we'll see later on how these different speed points actually influence the efficiency of the vehicle, because each of them correspond to different torque speed characteristics. Torque is operating points, which which really impact the efficiency at each of the points, okay, and the fuel consumption. Okay, now coming back to this, so it's a set of speed versus time typically, but the 1 minute, 1 minute, just. Hello, yeah, sorry about that. Okay, so as I said that it it's not just about representing typical road conditions and driving culture. It also tells you about the operating points that the vehicle, the corresponding engine or the motor has to go through, and then you can also, because it goes through different torque speed points, the efficiency, the emissions in the per unit kilowatt hour, or, so those things will change actually. The emissions per unit gram of fuel, right? So no, sorry, so you can convert that to any energy, so those things we can analyze, because at different driving cycles it will go through different operating points, and based on which different emissions, different fuel consumptions, different energy consumptions, whatever you name it. So typically these drive cycles were meant for analyzing characteristics for engine powered vehicles, but now growingly they are being considered to be analyzed for electrified vehicles. But there are definitely, yeah. Now there are two types of driving cycle. One is speed versus distance and speed versus time. So speed versus distance is not very common. You must have mostly seen speed versus time. Okay, and then you can have modal, and then you can have transient drive cycles, right? So the transients means there will be a lot of variations, and the modal means they will be having, it will be mostly constant or not so realistic, but you will have kind of like a smooth kind of profile for the drive cycle. Okay, so how are they characterized? They are characterized by distance. Now how do you say that this is a drive? So then what is the average speed of the drive cycle? What is the duration of drive cycle? This what is the distance that the drive cycle covers? So this is in a very top level way of characterizing the drive cycle. Okay, so these are just some of the drive cycles to name a few. NEDC, FDP 75, I think it means Federal Test Procedure 75 days. So it's a very transient drive cycle. So you can see that there will be a lot of accelerations, decelerations. Right? So a lot of changes in top speed points here, but not much here, right? As compared to this. Then you have the HW highway FET. So here you have a lot of transients, but here you don't. The speed never goes to zero. That is one thing. So that's continuously. It goes on a higher speed, and then the attractive demands. The attractive demands are always on the higher side. Okay, then this is our very modified Indian drive cycle. It is developed by ARAI, and mostly they use this for characterizing performance of vehicles and for doing all kinds of analysis of the performance. So here is the cold start cycle. This is the urban driving cycle. This is the extra urban driving cycle. So this is kind of like a modified or mixed Indian drive cycle. So it captures the typical behavior of that, but in a little bit simplistic way. Okay, and you can see things like the top speed is around 90 kilometer per hour or so, but not for a large portion of time. Okay. Now let us let us go from the external environment to the internal environment, right? So that's why I'm talking about the powertrain here. So the powertrain, what is this powertrain? Which is responsible for transformation of power from from the the place of propulsion all the way to the wheels, right? So then you have this engine, then you have the clutch. This is for a conventional vehicle. Then you have the transmission, then you have the propeller shaft, which moves at lower speed as compared to that, and typically, and then you have the differential, So this differential is used for not only has a single gear, but also it's used for negotiating curves, because these two wheels, they let's say it's taking a left turn, it's going like this. So the inner wheel will rotate at a lower speed, the outer wheel will rotate at a higher speed, right? And so it does that actually. Even the it's just typically it's a mechanical arrangement, but nowadays we are having electronic differentials as well. But it will allow it to do it. That's a little bit. It's I'm not explaining it in this study, but yeah. So it has plenty multiple internal gears. So there ultimately it's always a single fixed gear ratio, but inside there will be some rotational toothed wheels, so in which they will try, they'll try to help it to there's something called the spider gears and ring gear and all these things, and using that they'll be able to negotiate the turn. Okay, and then you have the axles, and then it goes to the wheel. Okay, and then the wheel meets the road, which where it has to overcome the inertia, it has to overcome the resistive forces. So this is how the journey of course, of the power that gets transmitted, and it also experiences there is some kind of experiences the loading effect because of the wheels. Okay, so am I audible, by the way? I'm just
Yes, sir.
okay. Yeah, I just mentioned that consider powertrain without engine and all. So driveline is all these things without the engine part. So typically it's a we can see that this is a mechanical system. So for electric vehicles, this clutch may not be there, and then we have the motor there. So typically we can analyze the second law of motion used to derive the models. The lower gear will result in higher torque transfer and higher torsion. Yeah. So lower gear, typically in a vehicle, lower gear has higher gear ratio, and the ratio is higher, and the multiplication that with the torque that is generated will be higher. The speed will be lower. Okay. Now having this powertrain in mind, so HEV is all about changes in the powertrain structure. Right? So nothing, the external thing typically doesn't change. Apart from that, but maybe with the charging thing, but typically HEV is in a very layman language. It has motor and an engine, right? And then there are different configurations. The one is the series HEV, in which the entire propulsion is through entire propulsion, the mechanical the is through the motor. So the engine is the engine behaves as a generator working on its optimal operating point, and then it charges the battery. From the battery, the motor is always powering, mechanically powering the output. The output of the motor, which is a mechanical power, which will power the wheels. But in case of hybrid, parallel HEV, which are the controls wise, it is a little bit more complex. But both the power produced by the engine and the motor, they are mechanically coupled. Okay, so that's why the control strategies are much more complicated as compared to a series HEV. Okay, so this is the need for HEV. So one is the fuel consumption. The why do you have HEV, right? So because the engine is consume a lot of fuel, so it's good to have some motor which will assist in such a way that you don't some part of it would be done you taken care by the electrical energy. Second is the emission legislation. There's a huge there you see that there is a huge pressure, right? Bharat 4, Bharat 5, Bharat 6. So I think we are quickly shifting to Bharat 6, and emission and then it is in line with the Euro 6 norms as well, and but I think there will be some still going on. I mean, we have not yet implemented those emissions. We don't follow those things. I mean, I think I have seen some very old vehicles with Bharat 2 norms as well. So, but we should go there because it affects the emission. They are not so stringent, and because of which too much emissions, and because of which you can see all the places around at least around India, right? Because of bad air quality. So this is again that because of the because of this electrical source of power. So then you'll be using less of engine, and then you can emit less emissions because of that. And it's just, again, the very simplistic way of saying there are different operating points in which the emissions can be less as compared to other operating points. Then this is also an important factor from the cost perspective. Several ratings or sizes of motor and engine. Okay, so several why? Because let's say that you had to deliver 100 newton meter of torque at the wheels. Let's say. So in the earlier the entire engine had to do that, but now maybe the 40 newton meter will be coming from the motor, and the rest 60 newton meter can be coming from the engine. Okay, so that in this way you can reduce the ratings of that, reduce the size of the individual motors and engine. Now, coming to the controller part, okay, so there is a supervisory controller for the hybrid vehicle. So that's like the brain of the vehicle, like just like a supervisor. So directly, it's not responsible for the motion, but indirectly it controls the engine as well as the motor. Okay, and it tells that what is the torque split, just like I mentioned here right now, right? That 100 newton meter. So how much newton meter should be given by the motor, and how much newton meter should be given by the provided by the engine. So it does that. It's an intelligent kind of hardware in which the software, based on certain logics, it will try to deliver the right amount of torque. Now, how will it choose? It will choose based on several criteria. Okay, things like the available fuel or available battery, that what is the SOC at that moment, what is the speed, is it low speed, high speed, right? Because at low speed typically the efficiency of engine is low, and but torque is delivered is also low, right? So all these considerations it does, and based on which it allocates the right amount of proportion of more torque between the motor and the engine. Yeah, so it's concerned about maintaining the battery limits as well. It's not just the BMS, battery management system, but it also is concerned about that. Whether I should not, suppose the SOC, state of charge, is quite low, then in that case it will not use the engine, it will not use the motor much. So it will say that no, the engine will take over. Then you have the drivability issue, that that's sufficient torque that is demanded should be given. Then you have the diagnostics. Okay, so it takes care of many faults because it interacts with many components, including itself. So there can be several faults, right? So which it can report, or maybe do some actions also by, let's say, it can disconnect some relay or something like that. Then you have interacting with other units like BMS, MCU, TCU, ECU, etc. So BMS, battery management system, motor control unit, TCU is transmission control unit, and ECU is engine control unit. So it will interact with these things to coordinate in a proper. It will coordinate them so that the entire vehicle moves in the best possible way. With less emissions, less fuel consumption, better drivability, all these things, and then in a safe manner. Okay? So that is the role of the supervisory controller of the HV. So there are different, now I'm talking about the software, the logic of the supervisory controller. There can be different schemes for this supervisory controller. One is rule-based strategy. The other is, so earlier they used to use rule-based strategies. So the other is equivalent consumption minimization strategy. The other is model predictive control-based strategy. So these things, strategy, the MPC is picking up big time, and BCMS has been used a lot actually in advanced hybrid vehicles. Okay, so this is some of the videos you can watch. Yeah, then yeah, this is a very simple thing. Typically, what are the electrified powertrain elements? You can have batteries, you can have motor with controllers. So this is why how it is different from normal conventional vehicles. Of course, you might have a small motor for uh, for startup and all, and for during idling conditions also. It will assist, and for powering the auxiliary batteries, so you have auxiliary motor. But I'm talking about a bigger motor which will try to assist in the continuously assist towards delivering the torque that is required at the wheels. Okay, and yeah, so what are the important things here? The important thing is torque speed characteristic derivation and model. So this is again important because that defines the efficiency at each point, and or rather for motors, and yeah, for engines, obviously I'm not talking about engines now, but the torque speed is again important. Then we can also talk about the losses and efficiency expression. So once we know, so this more typically the motors that are used for the electric vehicle traction are induction motor, PMSM, BLDC, along with their controllers. And then one interesting feature is the regenerative braking system. We can do regenerative braking also. Okay, so these are some of the components of HEV. Okay, so engine controller, motor and controller, battery and BMS. Right? So transmission, vehicle dynamics. So these are, so vehicle dynamics per se is not a component. It's a formulation kind of, it's a kind of characterizes the vehicle systems, and it talks about what is the longitudinal motion, what is the lateral motion, how the vehicle behaves. So this is very important for analyzing the safety of it, right? To see whether the, and also to see whether the vehicle is propelling to the required speed or not. And of course, the supervisory controller, which I've just talked about, it's a hardware board. It can be mostly separate. So these are, while these are all important, when, especially when you're trying to model a hybrid electric vehicle. And yeah, now coming back to the speed torque efficiencies point, you can see that if you have this engine speed and this engine torque, so this is the BSFC, base fuel, base specific fuel consumption. That means for each kilowatt hour of power consumption, this is the fuel. Yeah, for each kilowatt hour of for each kilowatt, it's just energy, so don't mind about that. So it's just a way of energy. And what is the fuel that is being consumed here, right? So how much fuel will it draw in order to give output of this much energy? Okay, so this is the mechanical output, and which is again converted to this joules and all, and then that joules is again converted to kilowatt hour and all. So you can see that this 250, these are different contours. These are different contours for the BSFC, right? And you can see that this 250 means 250 grams per kilowatt hour, which means the fuel consumption is the minimum. So if you follow this curve, if the operating points, to follow this curve of torque and speed combinations, then the fuel consumption is quite less as compared to this this curve. If the torque speed points belong to this set of points, then the fuel consumption is quite high, 400, right? So that's quite high. It's less than double, but it's quite high. Yeah, so even this 500, so it's totally double. So there's a huge difference. So the torque speed points are very important here. Okay, and this is the maximum torque envelope. See that this is the possible torque that you can have at different speeds. Okay. Okay. Then yeah, now coming to the motoring part. The motor also has similar kind of contours, but not same. Right? So it also has contours. Right? So here you can see that at this speed and at this torque, right? You have different combinations of these are the efficiency points, right? So the motor will exhibit different efficiencies at different torque speed points. So one would always like to operate them at these, along these contours, torque speed combinations, so that the efficiency will be more. So what does it mean if the efficiency is more? 1 minute, just. Hello. Yeah. Sorry about that again. Yeah. Yeah. So this is the torque speed efficiency curve. So these are again important for designing, or rather designing controllers, so that the torque speed of the motor will be at least close to these curves for contours, so that the efficiencies are the efficiencies are highest possible. Of course, it's not always possible, but so this is again, these are again important for the supervisory controller. So it will try to take into consideration these curves, and based on these curves, it will try to, it will try to, yeah. So torque split, so it will try to do the torque split between them. At what point, whether engine is more efficient or motor is more efficient, or so it will consider all these aspects. It will also consider the fact that the motor, let's say the torque total demanded. Let's say that each of the, let's say the motor is small, the engine is also small. So it will try to, it will also try to give the right amount of torque command so that the demanded torque is satisfied. So it will take care of all these things, but it needs knowledge of these things. So that's why it is very important to know these torque speed characteristics, both for the engine as well as the motor. Okay, and then yeah, so this will these curves will act as references so that you will be able to design the proper control strategies. Okay, so this is again a very generic structure of a hybrid electric vehicle. So the heart of it is the supervisory control unit, and so let's say there's an accelerator pedal, then you have the vehicle speed. There typically there are lookup tables which will say that, okay, based on this accelerator pedal, based on this vehicle speed, this is the total power that is typically to be demanded, and then they can be different. This is just a suggestive thing. It can be a heuristic based, lookup table based strategy. It can be a rule based strategy. It can be, yeah, as I told, mathematical strategies like ECMS or model predictive control. So there can be several strategies here, right? And then of course it takes information through sensors, right? And then it will and also diagnostics also. Diagnostics are also an important part of the supervisory controller, and it controls the motor, it controls the engine based on certain things. And then the, since this is a parallel HEV, so the mechanical output of the motor, the mechanical output of the engine, they get coupled, the transmission, and then the vehicle, and then it results in the vehicle dynamics, right? So you can see the, the relation between this vehicle dynamics and the powertrain, right? They are not decoupled, they are actually coupled, and both affect each other. Okay, and yeah, so that's how things are, yeah, mostly placed. But this is again a representative diagram of using the diagrams around. Yes, and then there is the other part is the transmission. The transmission will help the torque and speed points to be shifted, and that's why this transmission command will also be an important part. So typically it can be coming from the driver, it can be coming from the supervisory controller. So there's a transmission control unit, and then inside there will be a transmission hardware, and then it will be, delivering, then finally the net torque will be delivered. So there are different configurations also when how the motor and engines are placed. Okay, now let us go a little bit deep into the powertrain system. As I said that this EV, HEV, conventional vehicle, how they are the EV is actually different from a normal engine based vehicle by simply by saying that the powertrain is different. So how are they different? Because the powertrain is different because instead of engine you have the motor and controller, right, along with the battery. So that's why and then, as I said, that this entire thing, the vehicle dynamics and powertrain, all of them interact with each other, right? So that's why it's very important to understand the forces. It's, as I said, that it's not just electrical or mechanical, it's actually both, or rather it's all electronics, electrical, software, everything. So we need to understand so that we'll be able to design electric vehicles, not just the actually architecture, but also the control strategies. But so that's why, yeah. So that's why, we will go to this. This is nothing. This is nothing rocket science. It's very simple using Newton's second law. That it's force balance equations, right? So yeah, so the propulsion and braking performances such as maximum speed, acceleration time, gradability, stopping distance are the most important factors to judge in a car or in any vehicle. So for that, how do they happen actually? They happen based on the powertrain only. The powertrain only produces these things. So we need to understand the force relation. Right? So this is the, so you can say that according to Newton's second law, net force is equal to mass into acceleration. Right? That's how it happens. And this net force is the tractive forces at the wheels, the front and rear wheels, and minus the resistive forces. So the resistive forces can be due to the aero drag, the rolling resistance, and the gradient. Right? So this is how, yeah. So it's like a free body diagram of the car, and then you can see that it is yeah, so the based on, so you can see that there are different forces acting on it. And why is it important to understand? Because this will actually eventually act as load. It will result in load on the vehicle, and then the motor torque or the engine torque has to overcome these things. So in order for the car to move ahead. So, so this is the expression for gradient. It's nothing but mg sine theta. I think you must have read in your class 9 physics at time. And this is the gradient. This is the aero drag. Right? So the aero drag is half rho a. Rho is the air density. CD is the coefficient of discharge. AF is the frontal area of the vehicle. U is the speed. Then you have the mu. Mu is the coefficient. This is the mg weight of the vehicle. Then this is the mg sine theta. So these are, this is in whole. This is the total resistive force. So during acceleration, the powertrain produces positive longitudinal force by applying positive driving torque to the wheels. Now during braking, the friction braking system adds another negative braking torque to the wheels. Right? Or sometimes if it is regenerative braking, the braking torque comes from the motor, okay, to the axles, and then it will behave as a load for the axle. Okay, so two directions of braking torques coming. One is the mechanical friction braking torque, the other is the regenerative braking torque. Okay, and apply to the wheels and produce negative longitudinal force. Now here we can see again the torque speed characteristics. So why again I said that this is important, because let's say that we have so why have I slightly shifted actually? So this tells us the torque that is typically required here. So based on the forces, the torque has to be required. Now based on the torque, we have to talk about the torque split. Let's say I told you, right, that 100 Newton meter of torque is required. Now how to use, whether to use 50-50, whether to use 40-60, whether to use 60-40, whether to use 30-70, how to do that? So for that we need to analyze, let's say, each of the curves. So let's say for the engine vehicle, for the engine curve, the curves. So we'll be using typically this motor only at let's say lower torques, and so this is just a suggestion. So lower torque and from lower speed to higher speeds, but then you can have a power assist also, right? You can also have a power assist on very high torque and high speed parts. So you can have engine as well as motor for that. So you can have, typically in this region you can have engines also, right? So these are again like, kind of sound like a if then else, which can be easily captured in state chart, you know, state it's not state diagrams, it's flow charts, sorry, flow charts. Using flow charts also you can do if then else. If the torque, basically you can say that if there is sufficient charge, and the torque that the motor can deliver is, yeah, by the way, I think I have forgotten to tell you that just like engine maximum torque, we have the maximum torque envelope of the motor also, right? Because at different speeds, this is the maximum torque, and this is the base speed after which it goes into, let's say, constant power mode. That means with increasing speed, the the torque reduces. So at this speed, the motor torque cannot deliver more than this. Right? At this speed, the motor torque cannot deliver more than this. So these are again very important to understand. This is for basics. Okay, and then based on, so why is it important to understand? Because we can put them into different modes. The supervisory controller will say that okay, now there is not sufficient charge here, right? So I'll not use motor, I'll use engine, right? We can also use both if there is plenty of torque required. So only the motor, only the engine will not suffice. So we can have both the engine and motor. Then you can have regenerative braking. So you can have regenerative braking also, while it is only when it is trying to reduce the speed, right? When there is a brake pedal actuation and all. So we can have generating mode. We have too much engine torque, so some of the torque can be used up in charging the motor, right? Through as a generating action. So simple. So that's why we need to understand these situations. Now let us go to one case study after the other. So this is again a case study which it was presented. So it was based on the work I did in KPIT. I used to work in KPIT earlier, but then I'm still in touch with KPIT. And yeah, and I still guided some interns, and I interacted with some people. I worked with not just interns, so some industry professionals of KPIT R&D, and then we did something which was worth presenting, and we had some good results also. And we used we used practical data and practical setups for those things. So and it was just published, and it was presented in a conference, IEEE conference in Singapore. Okay. So the topic was automated generation of energy efficient drive cycles for electric vehicles considering limiting factors. Okay, so this is a very important thing, and it was verified also with the practical data from the vehicle. Okay, so what am I trying to say here? I'm trying to say that these drive cycles, I've talked about these drive cycles, right? And these drive cycles actually correspond to different torque speed points. So if we try to generate those drive cycles which correspond to better torque speed points, then we can have better efficiencies, right? We can have better efficiencies here. Right? We can have better, let's say that we're trying to have torque speed points which most of the time if they adhere to these curves which are having higher efficiency points, then obviously overall efficiency will increase. Right? So that is what the paper was all about. It's not a very complicated paper, but we got some good results. So I just wanted to share this. So yeah, so this was the case study layout. So now, so for that we need to understand the longitudinal vehicle model to understand what is the load, what are the loading conditions. Then you have the limiting factor calculation. Then you have the automated drive cycle generation algorithm, results and discussion, and progress. So I'll be just talking about these things. Now I'll be slightly shifting the gear because this is I will be now only talking about the electric vehicle. Okay, so KPIT has a bus called Revolo, and they had given that bus for testing, and we got some. We verified our simulation results with the practical results. Yeah. So yeah. So now let us talk about this electric vehicles. So they are first of all criticized for their limited range compared to conventional fuel-driven vehicles because there is always a range anxiety. So the problem here is that always when you do some research work, it is always about solving some problem. So the problem that we're trying to solve is, how to improve the range. How do you improve the range? By improving the efficiency, so that we can save more energy and then we can go further for the same charging. So, but the driving pattern also influences the energy consumed in the electric vehicles over a path. So that is because why? Because the moment the driving pattern, suppose I do a lot of acceleration, then the torque speed points will be different. I do less acceleration, again less torque. All different situations will come into picture. So the way I am driving has a huge impact. So that's why a simple framework was proposed for automatically generating energy efficient drive cycles, driving for a practical EV. Okay, so it's like a guideline, set of guidelines in which you should say that, okay, if you follow this kind of drive cycles, then if you follow this kind of drive cycles, then you can improve your energy, minimize your energy consumption. Okay, so now, but there is one problem, that the most energy efficient drive cycle may not be the fastest one. Yeah, so that way you can we use some weight factors based on time and energy. Okay, and such automated drive cycles, once generated, they consider requirements and practical constraints. The practical constraints, like I cannot have more than this much torque, I cannot have more than this much speed. So those constraints are that I cannot go beyond this gradient. Right, suppose we saw that the gradient causes this resistive force, these resistive forces. Right, these resistive forces, again, there is a limit to overcoming these resistive forces. You cannot go beyond something. If the gradient is too steep, then this mg sin theta component will be high. So the torque of the motor may not be sufficient to overcome that. Okay, so how to take care of this? So that can be computed to some extent. So the objective was to develop an automatically generating energy efficient drive cycles for energy based on longitudinal vehicle dynamics, limiting factors such as acceleration limits, jerk limits, minimum and maximum vehicle speed. So so that these things obviously it had to be very practical. It's not just you go to some you can just choose some random speed and torque combination and then you improve your efficiency. No, it should be within logical boundaries, or rather more practical boundaries. So there are there are always acceleration limits or jerk limits. So what is jerk? Jerk is rate of change of acceleration. So so all these considerations were made while generating the drive cycles. So there are several work, but not quite, not nobody had done exactly what we had done. So that's why we thought about making this. Okay. So most of the previous was done considering fuel-driven vehicles, and yeah, most of the time that you see is, as I said, it's quite different that we have what we have done. So they are because still people are still doing plenty of research in electric vehicles. That's why people mostly work carried on automated systems are mostly for engine powered vehicles. They have done all kinds of probabilistic based and gradient based and traffic conditions, you know. So now let us look at it closely. Again, we go back to our the beginning. Ah, sorry, somebody is calling me. Yeah, sorry about that. Am I audible? Yeah. Yeah. So let us look at it. So this we did for a electric bus, and we try to analyze what are the different forces acting on it. Okay, and yeah, so the rolling resistance force, then you have the gradient force, you have the aero drag, and then net force. We know that it's mass into acceleration. Right? So these are the expressions for the rolling resistance forces, and this is the actual expression for the rolling resistance. Sorry, this is the rolling resistance force, and then the gradient and the aero drag force. And then these drag coefficients were again given to us by the company, the R&D people, and then we use these coefficients, and we also this was the characteristics of the motor. This is the, if you see that the motor had a speed torque characteristics, right? That, and it had a maximum torque envelope. So this is in the very we cannot exactly give the motor's characteristics. So this is just a representation of this representation of the torque speed character. And this is the maximum torque that you can avail at different speeds. So you can see that at higher speed we cannot deliver more torque. So we have to consider these things, right, before talking about drive cycles and all. Right? So so this is not about the efficiency. This is about the maximum torque that the motor can deliver at different speeds. Okay, and now let's say that using these forces, we'll be able to know that what are the forces acting on the wheels, or rather how much torque is required, right? This FTR is the tractive force. So from the tractive force, we can convert that to the torque that should be provided by the motor, right? And from the torque that can be provided by the motor, then the torque at the motor will get multiplied by some ratio, so some coupling ratio, multiplied by the differential ratio, multiplied by the efficiency, drive line efficiency, and then finally you get some torque at the wheels. Right. So we know how much torque this motor is delivering, but what is happening at the wheels? So we have to multiply all these factors. Some transmission ratio, if there is, all the electric vehicles may not have, but they had some transmission ratio, then differential ratio and efficiency. Okay. So this is the wheel torque, and then coming to the motor torque. So typically, how much should be the motor torque? The motor torque is actually so it is based on the design of the vehicle and how much, there is a, again, it also had a supervisory controller, even though it was not an HEV, but so this it does many things, just like the supervision controller does things like the diagnostics, the torque speed and all. So here it will also give some kind of torque, but it will mostly be for the tractor torque because there is only one propulsion, and then there is this auxiliary. It will also be interested in the auxiliary part. Right? So here, so based on, so there was a map which said that based on this pedal, TPP is the pedal position, and V based on this speed, then this should be the motor torque that it should be giving. But this motor torque should be within this boundary for that speed. So that's suppose the current speed is, let's say, this much, the motor torque cannot be more than this. Okay, and yeah, so this is the torque at the wheels which are required to overcome the forces and make the vehicle move. Okay, now coming to the maximum gradient. So we know that it's balanced, right, based on force balance and Newton's second law, that net force is equal to mass into acceleration. So for acceleration to be zero, so that it is just able to overcome that, so we can calculate the gradient force, right? So that force which exactly compensates the, or rather balances the net force, is the maximum gradient force that we can have, and from that we can find out what is a theta max, what is a gradient angle we can have. So from this we can calculate that how much how much angle of steepness the vehicle can go up. Right? So this is again for a given drive cycle, right? For a given speed and all. So given the speed and drive cycle, we can get that. So for has to run at a full capacity. So for maximum gradient, so this is again for TR max, right? So considering that here the motor is giving maximum torque, which results in maximum tractive force, which then based on that, what is the maximum gradient that you can get? Okay, so you can find all these things. And then, so how can we get it? So we can do it through these drive cycles. Using these drive cycles, we can find out, we can characterize the drive cycle. That what is the acceleration we can have? Because we can see, right? We can see that at each point, we can see the speed at each time. T1, T2, T3, we can have speeds. So we can find out the acceleration rate of which is nothing but rate of change of speed. Okay. So, and using this acceleration, I alpha, rolling force, aero drag, and plenty of things, we can, again I alpha is again roughly related to the, or rather proportionately remote or directly proportional to the mass of the vehicle, but it's a little bit more complex there. I think somebody is sending some. Is there any? Okay, fine. Okay, so yeah, so based on that, all these considerations, we can also talk about the gradient force, and then using that, this is nothing but the representation of this, and we can find out the gradient theta versus time. So at each point, given the speed, so this is, mind you, this is the instantaneous speed we are extracting from the drive cycle, and corresponding to each of the speeds, what is at that speed, what is the maximum gradient that the vehicle can negotiate? Okay, so we can do these things thanks to the expressions. Yeah, so this is the coming to the maximum acceleration that it can have at a different for a given gradient profile, right? So see, this is so we cannot have two variables for a single equation. So we're keeping one, assuming that something is known. So what should be the other value? So for a given gradient profile, let's say that we know that the vehicle is moving up a gradient, and we know that what is the gradient there. And then for a given, obviously for the maximum possible tractive force, because of the maximum torque that is possible to be delivered by the motor, what is the maximum acceleration that we can achieve, right? So this, why are we doing this? Again, we try to find out the maximum acceleration so that we don't exceed the acceleration that is given. And again, using this very simple thing, right? V dv, right? V dv by dt and ds by dt. So you can just, this very simple mathematical jugglery. Speed is equal to ds by dt. The speed, s is the distance, so ds by dt, and acceleration is equal to dv by dt. Right? So you can do this. So that means from 0 to this speed, and from 0 to s, right? So so this is the distance. So that means we say that when it is going from 0 to v speed, the distance traversed is from 0 to s distance. So what is that? Uh, so what is the maximum velocity from maximum acceleration? So using the maximum acceleration can be using law of motion. Okay, so how can we do this actually? So we just have to keep on integrating both sides. So we know the speed profile, right? For the speed profile we know, and from this, so what is that? What is the set of? So this will be helping us in generating the curves, the speed curves, so that we're generating the speed curves, so that we will know that at different, what are the different accelerations we can have. Sorry, what are the, we can, first of all, we'll have these. So we're trying to generate, has to run at full capacity of motors. So we can generate a lot of things here. So we can see the speeds, we can, so this is just the relation between the speed and the accelerations, and how we can, this will help us in generating the yeah, this will help us in generating the one minute. Yeah, sorry once again. Yeah. Yeah, so this will actually, this will help us in shaping the profile, which is not directly mentioned, but there is, we have developed an algorithm. So using this concept, we generated the driving cycles that is best possible, which will go through the best optimal efficiency points for that. Okay, now, yeah, so now similar to the gradient part, we could find out the acceleration part also. That what is the maximum acceleration given a gradient, maximum given a gradient force. So once we know the gradient, we can find out that we can find out the acceleration and maximum acceleration that is possible. So this will again at each point this will govern, because we will be generating these drive cycles. I'll just do some forward referencing here. So we are actually we'll be generating these drive cycles here. What is it? Yeah, this kind of drive cycles here. So these drive cycles will be generating, but we know that what is the maximum acceleration we can have, right? So this will help us in this governs the maximum limit on the acceleration that we can have. This tells us that at this gradient, what is the acceleration. Similarly for this, what is the maximum gradient we can have. So all these situations will be helpful in that. So we develop these algorithms. I think in the interest of time, because we have to just talk very briefly about this. So based on we keep on generating these torques, right? We keep on generating these speed points. How do we do it? We do back calculation from given a torque. right? So let's say that some torque is required. So this is the T min, and there will be some ratio fraction of the maximum torque, right? Also from there, we are so from there we are trying to find out that what is the in order to satisfy this torque, what is the acceleration that we are getting. But in order to have that acceleration, is it exceeding the maximum acceleration that we just computed? Then for that acceleration, again, we'll also talk about the jerk, because the jerk is the rate of change of acceleration. From that, again, we'll find out after the acceleration, we'll talk about the speed, right? Then from the speed, we'll find out the distance that it will be traversing. So this is an algorithm which we developed, and from this, we generated the drive cycle. So this is the drive cycle. Automatically, it keeps on generating, and this drive cycle will be actually behaving as a reference for a driver. So this is the set of, maybe I'll share the slides also. This is a set of points in which you can keep on generating that. And of course, we can always say things like the torque divided by efficiency, right? So because the torque gets affected by once it is traversing from the motor to all the way to the wheels. Similarly, the deceleration also similar, but the deceleration happens in the opposite direction. Just like you have torque divided by efficiency, here you have the torque multiplied by efficiency. So the torque traverse. So this is obviously this is the mechanical torque, and then this torque, it gets multiplied. The mechanical torque at the wheels, it traverses, it gets converted from the torque speed, mechanical torque speed, then it gets converted all the way to the battery. So the mechanical power, in case of regeneration, the mechanical power gets converted to electrical power. Okay. Now, using these algorithms, we could generate plenty of results. So, but before that, we were actually using an actual electric bus, and because of the electric bus, we had to ensure that whatever model we're trying to which mimics the actual vehicle, mimics the actual vehicle, it uh, you know it should be able to match as closely as possible. Then only we'll be confident in saying that, okay, whatever model we have developed, it is mimicking the actual real system. So that's why we use these parameters. These are real parameters from an actual vehicle, and then from motors, the frontal area, differential ratio, tire radius, drag coefficient. So all these things were actually given to us by looking at the vehicle and all. And then we use the same motor. You can see the motor rating, everything. We use the same. We used in the same equations, and surprisingly, it matched very, very well. Okay, so one is the real electric vehicle data which we gathered, and then the other was the model data. You can see that. Which we gathered from the vehicle, and then the other was the model vehicle. You can see that both are matching. They are matching more than 95%. Okay, so because it is short, there are some discrepancies here. If you see, there are some discrepancies, but it is quite the entire trend is matching. Okay, so what we did was we used the same equations and we use the same parameters, and using this model, we were able to match this. So they verified the accuracy of the model. So once we verified the accuracy of the model, we had the confidence that since it is behaving like the vehicles, then we could do all kinds of operations on it. Right? So we used it just like the vehicle. And so we used in different drive cycles. So one was the Mumbai drive cycle, the other was the Delhi drive cycle. Okay, and then this was the velocity profile for the Mumbai and the Delhi drive cycle respectively. And these were the different gradients that we could say that, look, this is the this is the gradient that can be possible. Even this is again negative gradient. In order to, so this is in order to sustain this kind of motion, right? In order to sustain this kind of motion, the gradient, you can see that the gradient cannot possibly be positive. It has to be negative. Even zero is not sufficient also. That means at very high speeds, right? At very high speeds, the motor, the tractive torque of the motor is not sufficient to generate result in this speed. So what do we need to do? We need to have a negative gradient also in this space. That means so that the extra traction will be provided by the negative gradient force. Yeah, similar to the Delhi drive cycle also. You can see that the bus that we saw, that is not very sufficient for let's say for daily drive cycle, for daily drive cycle, right? Even because this is quite high for, but then we need some kind of we can need some kind of negative slope so that it will give some extra traction force. This is what we analyzed. Yeah. So now this is the maximum velocity. So similarly, we could also get the at each of the points. So for a given gradient, what is the maximum gradient velocity that you can achieve? So we could compute all these things. Okay. So, yeah, and drive cycle generation data. So this is different. So we generated. So all these using all this analysis, we could generate the we could generate the data. Okay, so what is the data we generated? We just generated the speed versus time profile, and it was nothing but the set of accelerations and decelerations. Okay, so we iteratively did that using these algorithms and considering the upper and lower speed limits. Okay, and we generated these drive cycles. So there are different types of drive cycles, smooth drive cycles, and then mini drive cycles, which are more efficient. So how did we do it? We kept on choosing those speed points so that it will correspond to those clock speed points, so that the efficiencies are in the optimal as much as possible, maximum possible regions. Okay, and there are some of the observations. This was the weighting factor. So we had used some weightage factors to say to talk about what is the ratio of maximum torque that we are using, right? So this is the one means we are using maximum torque, right? So but then when the higher, you can see that at different weighting factors, with zero weighting factor, the time taken was quite less, so it's quite large. Okay, so less torque, very less torque, and the energy, but the net energy consumption was quite low. But in this high torque, when the weightage factor was high, then the net energy consumed was quite high. Okay, so it is somewhat inversely proportional. Okay, so now, so this method of generating energy efficient drive cycle by minimizing energy consumption while decelerating can act as a guideline for drivers beforehand. Okay. Okay, so drive cycle generated through proposed method may not be the most optimum drive cycle, but can help in saving considerable amount of energy. Like I said, that it's a, we cannot have both the things, right? We cannot have we cannot have. So you can see that it's roughly inversely proportional, right? If you have less time taken to cover the drive cycle, then the energy consumption is high. But if you have, but if the energy consumption, you want less energy consumption, the time taken was quite large. Okay, so this is what we observed in for our situation. So it cannot be, we cannot have, it's a mix from both the worlds, but we cannot have exactly have the best energy consumed and the best time taken, right? There will be some kind of compromise. But then we had the choice that if somebody is interested in, let's say, reaching home early or reaching the office early, then we can suggest that kind of drive cycle, so that the time taken will be less. Similarly, if the person is interested in having doesn't bother about the time, then we can use the weightage factor to generate that kind of drive cycle, so that so this is, so because of the different weightages, different drive cycles were created, but ultimately it is the same distance. Okay, I think my mistake at all. It's not the same drive cycle, but it is the same distance. The distance is the same, but the integration, the integration of the area is nothing but the distance. That is the same. The area under the curve, the integration of the speed profile is the same. So we can choose all these things. So this is given to the option is given to the driver, that if W is equal to 0, then you can have best possible energy consumption. But if W is on the higher side, that energy consumption will be high, but time taken will be quite low. Okay. Now, so this is so the final thing is driving patterns do affect the energy consumption, and that's what we have proposed. And then of course it's a known fact, and we generated some drive cycles which will help us in doing this. Now coming to the second case study, I think I'll be able to cover two case studies today. So this is again this is related to electric vehicles, but it's a very interesting topic. It's on the predictive supervisory controller for an HEV operating in a zero emission zone. Okay, so in different places, parts of places like Europe, I went to, I think UK, I saw that there are some places called low emission zones. So in those cases, and it's coming up, I think it might come up in India also, that those places you don't want emissions because of some safety, I don't know, some hospitals or maybe child care or something. So what to do then? In that case, suppose you have an HEV that you are operating. So you want that HEV to in that, suppose when you go to that zone, that physical zone, you want that HEV to, by the way, it was this was again a conference paper which we worked with Tata Motors, and then we developed the strategy, and it was presented in ITech conference in Detroit, Michigan. Okay, and they also said it was quite interesting. So what is it that we're trying to solve? We're trying to solve the strategy. We're trying to make a strategy so that the HEV will save enough energy so that the moment it goes to the zero emission zone, it can afford to become an electric vehicle. It might so happen that, let's say that it is traveling, right? Let's say that it is traveling here, right? So I'll be talking about that later. So I just wanted to tell you about this, so that there is a drive cycle here. Okay, so this is a drive cycle here, and then and this is the zero emission zone here. Okay, this gray area. Now, the moment, by the way, it might so happen that if you have not taken proper caution, or you have not considered anything, let's say the HEV was, working, and the moment the HEV was working, and the moment it reached here, the HEV can no longer, it says that, oh, my battery has gone down, the SOC is not enough, right? So if the SOC is not enough, then it cannot behave as an electric vehicle. Then the engine has to kick in, and in that case, all hell will break loose, right? Because because the engine will start operating, and the emissions, it will be a typical. It will not be a zero emission zone. It will be a full emission zone, right? Because why did this happen? Because enough charge was not saved. So that is what we are trying to do here. We are trying to develop the supervisory controller in such a way that it will know in advance that, okay, after 5 to 7 kilometers, there is a zero emission zone coming. So before I reach this 7 kilometers, I should save enough electric energy so that after I reach this zero emission zone, my HEV can afford to operate as an electric vehicle, pure electric vehicle, right? Because HEV has different modes, right? HEV can work in electric vehicle mode, it can work in pure engine mode, it can work in both electric as well as engine mode, is hybrid vehicle mode. And so that is, yeah, so that is what we try to harness. Okay, so the problem is requirement of HEVs in Indian market, introduction of low to zero emission zones in Indian roads. So maybe in the future part, I think the government might be imposing some zones and saying that, okay, these are low emissions or zero emission zones to preserve the quality of the environment. Then conventional energy management strategy. So we started with a conventional energy management strategy, which is called the yeah, we'll come to that. Then modifications on the conventional energy management strategy. So as I said that typically, let's say in a Toyota Prius, people used to use, and they used to use, I think they still use the rule-based strategy based on the experience that under this situation, you use it and the engine, you use the motor, you use both. So we used another conventionally used engine management strategy called the ECMS, equivalent consumption minimization strategy. We improved it in such a way that we could achieve that thing. Okay, so modification, that's what we did. We modified it. So here we see, let's say this black one is the drive cycle, which the vehicle has to yeah, so this is the vehicle, the drive cycle that the vehicle has to move. Now the moment it is accelerating, what is happening? So SOC, state of charge of the battery, it is reducing. So I'm not concerned, not much. I'm not talking about the fuel. I am assuming that I have enough fuel, but the energy, but because the fuel density is higher, right? The energy density of fuel is higher as compared to the battery. So But what is happening is because of the acceleration my SOC, we actually simulated this, and we sort of found out that because of the acceleration, the state of charge is reducing, right? Then, then, then there's a deceleration. Because of the deceleration, we did some regenerative braking there, and we could save some energy. So by the time we reached this zero emission zone, we had enough energy here, electric energy, to sustain. And then what happened? We used as a pure EV, and what happened was, because of this regenerative braking still continuing, the energy kept on building up. But after this, it was acceleration and cruising, so which more or less consumed energy. So we completely used it in the EV mode, and then we, kind of used it in the EV mode, and then we then by the time the zero emission zone ended, by the time it ended, this became it became the SOC went to SOC minimum. So you can see that it reached. So what did you do? Because we could estimate in advance. So this is something called predictive control. Okay. So we predicted in advance that if you have this kind of drive cycle, if you have this distance, if you have, based on the speed, we can see that what will be the torque. Based on the torque and the speed, we can find out what is the power, mechanical power, that is required at the wheels. From that, we can compute backwards. We can see that based on the computer, we can see that this is the energy consumption. Based on the energy consumption, the power, instantaneous power consumption, we can find out the energy consumption, and that this way. And then this way we'll be able to do the zero emissions. And it is, and by the time it reached this distance, it was just enough, right? And so we kind of optimized it also. And we did some other things also. This was some buffer zone. It's not like the moment it the moment you can see the emissions also. We estimate, we used advisor's model simulator. It's called advanced vehicle simulator, and it is used in several places, and it's a standard industrial software, and many industries use that, and it is validated also. So this is the red part is the emission. So it's a summation of these carbon dioxide, carbon monoxide, sulfur, all these things. And we can see that we used the supervisory controller used the torque speed strategy in such a way that the emissions tapered off, right? It should not be that suddenly the emission is not there, because it might so happen that the wind can blow and all. So there was something like a buffer region. Okay, so the buffer region helped us to kind of like a taper it off. Similarly, taper it on, so that it can happily again, once the zero emission is going far and far, then it can again go back to the it can again go back to the higher. It can start polluting again once again, happily, without nobody disturb. But then this is what we designed. Okay. So now, so let us talk about. So this is the P2 HEV architecture that we considered. So as I told you that HEVs have different architectures, series, parallel, and I think I forgot to mention combined series parallel architecture is also there. But here we are considering only the parallel architecture, and that too in parallel there are different ways of configuration. So we use the P2 HEV architecture. Okay. So this is the P2 HEV architecture, and so here there is an axle. The torque, engine torque, and the motor torque, they are coaxial actually. So deliver the torque in a coaxial manner. And this is the clutch, this is the gearbox, and this is the differential, and this is the axle. These are the parameters that we used. Okay, each of the cell voltage is 1.2, vehicle mass 1000 kilograms, and all these things. And so basically what is happening is the motor and engine torque both deliver contribute to the torque demanded demanded torque at the wheels. Okay, and we can have different kinds of there is another there is another clutch here that has not been mentioned yet. So we can have different kinds of configurations here, and then we can have motor turn off and only engine. We can have engine turn off and then the motor. So there is a clutch there because suddenly we cannot turn off the engine. so that then you have the motor only contributing to this, or we can have both, also both contributing to that. Okay, so this is again the block diagram view of the controllers. Right? So you have the engine control unit, the battery management system, the transmission control unit, the body chassis, and ABS anti-lock braking system. You have the motor control unit, right? And this is the powertrain. So these control units talk to the powertrain. They control the powertrain. They take feedback signals through sensors, okay, from the powertrain. And yeah, these are the typical commands, and ABS commands. The I is the gear ratio command. State of charge, it will just take what is the state of charge. The torque command, the motor torque command. So all this will be feeding back. The powertrain will also feedback something. So this is the energy management system, which will be running inside the supervisory controller, and using that it will be operating. Okay. So this is again, I think I have told you about so while choosing this supervisory controller, we were looking at the motor efficiency contours as well as the engine efficiency controls. Okay, so these efficiency points that we got, these are some of the we consider these efficiency points, saying that with this torque, this speed, what should be what should be my operating point, so that it is well within that best efficiency, best possible efficiency point, or BSFC point. Similarly for the motor part also. So this is again, you can see that these two are symmetric, because this is for the regenerative part, right? So here you have the negative torque for the same speed. So this is for regenerative braking. So typically they are mirror images of each other. So the characteristic profiles are nearly the same. Okay, so let us now look at this. So what is happening exactly? So there is a driver. The driver says that at this speed I'm giving this much pedal. So based on that, the supervisory controller says, okay, this is typically the torque that you need, and it splits. It says that, okay, so it looks at this speed, what is the torque that I can take from the engine. At this speed, what is the motor torque that I can take, and what torque I should choose, so that the efficiency points are possibly best. Similarly, what is the torque I should choose from the motor, but at the same time, both the torques should add up to the total required torque. So that is also a factor. Right? So similarly, and then this will be again fed to the automatic transmission or the normal transmission, and then that will be delivering torque to the vehicle, and the vehicle will deliver motion, right? And then there will be a speed. A driver will be happy or not happy with the vehicle, and then it will keep on giving pedal command. So it's like a driver in loop. So this is like in a closed loop control system with the driver also. Yeah, and then it will be checking other things like the battery SOC, right? And other things. Yeah, so this is in short, this I have talked about. This again I have talked about. This is ECU's engine control unit, ECU's transmission control unit, the powertrain. They interact with the powertrain components. Okay, and this is the CAN bus structure. So there is something called the control area network. Typically, vehicles have this CAN structure of they're interacting with different controllers. So the controllers connect through these buses. Okay, so they have typically these CAN signals have these high-low things, and they have the frame format through which they convert. They transfer messages. Why? Because let's say that why? Because this is very crucial, because you have plenty of sensors. Let's say hundreds of sensors. So, and the sensors carry information. And let's say the transmission control unit requires the speed, right? But the motor control unit also needs the speed. The engine also needs to know the speed. So you cannot have separate sensors for each other. But or else, or rather the same sensor, if you connect it to all of these things, it will be again there will be plenty of there'll be plenty of problematic things actually, because there'll be too much of wires will be jumbled. So that is why we have these CAN buses. So they communicate from one controller to the other. Okay, so so that let's say that let's say that the transmission control unit, right, there it was connected to some speed sensors. So the speed information through this CAN bus will travel to all the other control units which are connected in the same bus system with the transmission control unit. Okay. So this is again, then you have the BMS also. So this is this communication. So CAN is again a controller and has a communication protocol also. So through some frame forward format, they'll be communicated. Okay, so they have something called the CAN matrix, right? So from the CAN matrix, you'll find out that what is the how the message, what are the different messages, what is the if the message is periodic message or one-time message, what kind of messages are we talking about. So all these things will be considered there. So this is again the electronics part of that, and which obviously interact with the mechanical part also. So that's why it's called mechatronics. Right? So you have the mechanical things like the transmission, the clutch, the motor, the engine management system or the engine control unit. You have the battery management system, and then these controllers, they control the hardware or the mechanical things. So that's why they interact with each other. Parameters of Honda Insight model. Okay, and yeah, so this is the model that we used. So this was for this motor and having motor and engine, and then we use this strategy. Okay, so this was the engine consumption minimization strategy. So why is it called engine consumption minimization? Sorry, energy consumption minimization strategy. So this will make a cost function, so that we'll try to minimize that cost function. And in order to minimize that cost function, what should be the value of motor torque and engine torque, so that this cost function is minimized, right? So now, so this is again, so we need to, so this is what this algorithm is all about. It's a simple algorithm, right? So if you remember that we had this challenge of determining what should be the torque split, right? So let's say the total torque at the wheels are 100 Newton meter. How much should be coming from motor? How much should be coming from engine? So what should be the torque split between them? So this cost function will actually help us to determine that. Okay, and this was some weighting factor. Okay, so equivalence factor it is called. So let us now little bit dive into this equation. So this is the, let's say, the equivalent fuel consumption or energy consumption that we are talking about. So this is the battery mass of battery, or the power, or rather the power, the instantaneous power that will be consumed from the battery. So which is nothing but, what is this battery power? So this Tm into omega m is the output mechanical power of the motor. Okay, and what is, if you divide by the efficiency of the motor, you'll get the input electrical power, right? Isn't it? So what is efficiency? Efficiency of the motor is nothing but output mechanical power by the input electrical power. So if you divide by efficiency, we'll get by input electrical power, right? So this input electrical power will convert it to equivalent fuel consumption, and we'll say we'll divide by the lower heating value of the fuel. So this electrical power of the motor will convert it to the fuel, equivalent fuel. Okay, so these are all equivalent quantities. And so this is a standard algorithm. And this is the fuel consumption. This fuel consumption is also, it is the input to the engine. Now that also depends on the power that the engine delivers. So let's say that TE into omega is the mechanical power of the engine. So based on the BSFC, we can, BSFC is actually inversely proportional to the efficiency of the engine, right? So if we invert it, and we will get the efficiency of the engine. And if you divide by the efficiency of the engine, so we can either get it in terms of we can either put it in terms of fuel consumption, or it depends on how this is structured. If we have to either multiply with the BSFC or divide by the efficiency. So that if we divide by the efficiency, we will get the energy, electrical energy, equivalent energy. And if we multiply the fuel consumption, we'll convert it to fuel. Okay. So yeah, so then this way what we did was we multiplied with this, we divide by the efficiency, again we multiplied with this lower heating value, so that this will be converted to the equivalent fuel, mass of fuel. So then this is the cost function which we'll try to minimize. So this cost function will be minimized, and then upon minimizing or optimizing, then the values that we get for TE and TM will help us in determining the engine torque and motor torque that we should be giving. Okay, and then these are the constraints. Okay, so these are the constraints that we have to see, that See, we'll optimize this, but we have to see that the battery SOC should not go below the minimum SOC. Similarly, the battery SOC cannot go maximum. So typically, the battery SOCs are 0.8, 0.2, and 0.3. Hello. Hello. Yeah. Hello. Are you trying to say something? Hello. Okay. Yeah. Now these are the constraints that while optimizing we have to take into consideration. So this was the penalty function. It's kind of like a weightage function of the motor. Okay, and then we developed this to some, and we developed it further. You can see that when current SOC is more than the target SOC, S will penalize the cost function so that the motor will discharge the battery more. Similarly, when the current SOC is less than the target SOC, S will penalize the cost function so that the motor will charge the battery more. So this is the way in which the torque speed will be developed. Right? The torque, engine torque, the motor torque will be developed. Okay, so this is I have already talked about. So this is what we'll be doing. So from the beginning itself, we'll be doing the torque speed strategy on the supervisory controller, so that by the time we reach here, we'll have sufficient state of charge. Okay, we might have to there might be sufficient fuel, there might be ample amount of fuel consumption, which obviously we have to compromise, but while we are here, we should have enough stored in an electric charge so that we can sustain it as an electric vehicle mode. Okay, so this is the concerned this is the concerned emission zone that we are talking about. Okay, these are the buffer zones. This is the SOC reference. Okay, so we should have. And this is the leading, this is the leading buffer zone, and this is before the leading buffer zone. Okay. Okay. So from here, actually, here there are different zones. What we did from here to here, we were kind of like a happy-go-lucky kind of person. We did not bother too much about the SOC. So that's why you can see the SOC was going down, because we have to traverse the distance, right? But from here, we became very cautious. We started saving the electric energy. We started saving some of it was we started converting the engine to power into electrical power, and we converted it to battery power, battery energy. So that we kept on integrating the power and kept on saving into the battery, and that's led to the increase in the SOC. Right? So by the time it reached, it had sufficient SOC, and then it further increased. Right. So this was a no worry zone, but from here we started being very cautious, and then we had this increase the SOC to the required level. Okay, and then these are different modes. It went into different modes: state 1, state 2, state 3, state 4. So different these are different zones. We demarcated into different zones, and then everything was more or less working. So this was the algorithm which we did. We torque demanded over the drive cycle. From each of the drive cycle, we computed. We know that based on the speed and the gradient and everything, we'll be able to find out the torque demand. And from the torque demand, we calculated that what should be the SOC in order to deliver that much amount of torque. And then calculation of the Dmin, right? What is the Dmin? What is the minimum distance from which we'll start? What is that minimum distance from which we will, start being very cautious? Calculation and then calculation of Dmin. Okay, so this is the calculation of Dmin. Then after calculating, a lot of our work is done. So we know that from Dmin distance, we will start using the supervisory controller in a more specialized way, so that we'll start saving more SOC to sustain us in the zero emission zone. Okay, and then so this was, if we went through all these zones, and then we used different modes. We changed the formulations, the optimization formulation, and then we could achieve this. Okay, so this is, in the interest of time, it will take maybe plenty of time to explain. So anyway, so I'll just cut it short and I'll talk in an overview. You can refer the paper for more details also. So we could, so from the zero emission zone, we found out that what is the force at each of the instance, what is the force that is required to drive it in the zero emission, to drive the vehicle. And from that, we found out the torque that is required. And from there, how did we find out the zero emission zone force? We use this mdv by dt plus aero drag plus rolling resistance plus gradient. We assume the gradient was zero. And we could find out the motor power that is required. So from torque, we could find that at that speed, from the torque, we could find out that this is the speed. And from there, we could find out that what is the power that is required at each instance. From the power, we could find out what is the energy consumption throughout this distance by integrating throughout this region. And then we could, the moment we saw the energy loss, from that we could compute back the SOC reference also. Okay, so this SOC reference that we got here, based on the, so this current is actually coming, so this current will influence the SOC, but before that current is actually proportional to the power, right? So from the power we could find out the current, and for the current we could subtract and keep on understanding that what should be the my SOC reference. So there is a lot of back calculation here. Okay. Using this back calculation, we develop this algorithm, another different kind of algorithm, and considering the regeneration, the motoring regions, everything we considered, and we could come up with the minimum, the dmin, the distance minimum from which you will start becoming cautious, and in which you will execute our special supervisory controller. Okay, so this was our supervisory controller. So this was the same cost function that we used to optimize, but we used for different regions. So you see, these are nothing but the region 1, region 2, region 3 and all. We use different factors here. So that changed the formulation here. And using that, the aggressiveness of the supervisory controller was changed, right? So these are the different formulations which have helped us to achieve the result that we'll be seeing now. Okay, so one hard constraint or one equality constraint is that the net torque should always be equal to the engine torque and the motor torque, right? And both of them should be the optimal part, right? Both of them, the values will be such that the losses will be minimum. Okay, so this was the equality constraint. Now, using this formulation, I'll just talk. I think the time is okay. Yeah, so in the zero emission zone with any DC drive cycle using normal ECMS strategy. So there was, as I said, there is already existing economic consumption minimization strategy, and using that we could, using this equivalence consumption minimization strategy, we said that let's see what is the performance here. So we did not use our specialized modified ECMS strategy. We just used the plain ECMS strategy and see what was the purpose here. And then we saw this is the drive cycle, and it was more, it was here till here, because this is the zero emission zone. Till here it was matching properly. But, and this is the torque split between the blue one is that of the motor, the red one is that of the engine. So these are the values of the instantaneous value of the torque that have been provided. Okay, and but we see something bad here. What is it? That the red one, the engine is still providing torque, which we don't want, because the moment engine operates means emissions are happening, which is not a good thing. And later on again the engine, which we did not bother, but here this was very troubling. And then the SOC also. The SOC, you can see that the SOC was, why did this happen? Because the SOC was not sufficient. The CMS strategy is not intelligent enough to save sufficient electric energy in the battery. It doesn't do much prediction, it doesn't do anything. But what we did was, this has a lot of prediction elements into it. We did a lot of prediction, and based on which we could save, so that we'll see now. Okay, so this is the, as I said, this is the normal ECMS strategy. And so this, it's hanging. Yeah. So this is the normal ECMS strategy, and you can see that here that the engine torque is not zero, and but the emissions, obviously because of the engine torque, we are still having emissions in the zero emissions region. The battery is being used, but not that much. Okay, because you don't have too much of SOC here. Why? Because the SOC has dropped to a very low level. That is the reason why. Okay, so that's why we had to use plenty of engines. You can see the plenty of high values of engine torque, which resulted in plenty of emissions. Okay, so we could not use it as a pure electric vehicle. Okay, and then obviously later on the emissions increased further, and then the fuel was also not zero here. The fuel consumption, so that was not good. So this normal ECMS strategy did not serve our need. So then what did we do? We used our modified ECMS strategy, and you can see in this modified ECMS strategy, uh, even though, so here in order to satisfy the speed demand, it had to compromise on the engine usage. But here it is able to, you can see this red is completely zero. That means the engine torque is zero, because of which the fuel line is flat. It is not increasing the fuel consumption. The battery is being used. That is purely now this zero emission zone. The HEV runs in the zero emission zone in a pure electric vehicle mode, which is what we wanted thanks to the modified ECMS strategy. How did this happen? Because it predicted in advance. So it did predictive control. It predicted in advance. It controlled the torque strategy of the supervisory controller in such a way that that it could save sufficient amount of SOC. You can see it had sufficient amount of SOC here, and so that it could afford to discharge it and then use it as a pure electric vehicle mode. And you can see the emissions also, right? Around the emissions also quite low, right? Around the vicinity it has started increasing, but these are the buffer zones, so it's okay, right? So but here the emissions were completely zero, and it could afford to do that. So that was the beauty of our technique. Okay, so then this is the comparison between ECMS and both of them together, ECMS and normal ECMS. So one was a zero emission zone. This is the ECMS. You can see that SOC has dropped down. It could not save for a rainy day, but here the SOC was sufficient. So this is just together. So you can see just celebrating the success, nothing else. And then this is using a different drive cycle. Okay, so there's a different drive cycle using ECMS strategy. Again, you can see that here you have still some fuel consumption here. It was somehow in this drive cycle it was able to manage to some part, and then it was not sufficient. You can see this is the desired speed, right? So it could not deliver sufficient torque to overcome to track this speed, right? And because of which the vehicle HEV ran out of the battery, and because it had to use the engine. So that's why you can see that the engine was used, right? The SOC became zero, not zero, very low, below it became equal to the minimum possible. 20% is the minimum we have taken, and then after that it gave a torque, right? After that there was a after that it was forced to deliver the torque in order to satisfy the speed. Similarly, the battery also went, obviously the current, we were not using the battery because there was hardly any charge left, but we used the battery only for regeneration to absorb more charge. And you can see the fuel went up, so which was undesirable. So till here it could manage, but after that it could not do it because this is a normal ECM. It did not predict in advance. But the modified ECMS strategy for a different drive cycle, it could do it, right? So you can see that it's completely zero. Emissions are zero in the zero emission zone. So this is a distance based. So typically you can see time based, but this is a different base. I just wanted to observe that. You to observe that. And the battery, obviously the battery current also was quite high, but thanks to the fact that means it was delivering sufficient amount of torque, right? So you can see the engine torque is zero, but the motor blue torque is quite it's around 25 Newton meter or something. So it was sufficient to do that. But then you can see that here it is compromising on the speed, right? It is saying that okay, at least even if I'm not able to satisfy my speed, but at least I'm not using the fuel consumption, right? I'm not using any fuel, right? I'm not I'm not there are no emissions. I'm not, so that is also a compromise, right? So I'm saying that I'm not producing sufficient torque. So why I could not produce sufficient torque? Because my SOC was, because I had to save for a rainy day. I knew that in order to go there I'll be consuming this much SOC. So that's why I gave less torque, and so that it was able to deliver just enough speed, right? You can see the speed, it is just giving some minimum sufficient speed, so that basically it was going at lower speed than the desired, but it did not emit any emissions, right? So the fuel also were consumed was very low during this region. Later on it again picked up, it was consuming fuel later, and it was zero emissions, right? So that's perfectly fine. Okay. So again, using these are again the comparison between those things, and these are the numerical results that we got, right? The fuel consumptions under different drive cycles. You can see that using the modified equivalent consumption minimization strategy, the fuel consumption was less for any DC, right? Little bit less. Okay, 0.1 liter less. This is quite substantial. And for the US 06 also, it was quite less. For different drive cycle, we could reduce the fuel consumption, and at the same time we could also allow the vehicle to move in pure EV mode even in the zero emission zone, right? And then similarly, the fuel consumption was, you can see in kilojoules, it was like this. Now the total energy, but the total energy consumption, you can see it is higher. The fuel consumption minimized, right? The fuel consumption is minimized, but the total energy consumption. Why? Because we used more of motor, less of engine, but overall energy consumption. But that's fine. But we could use less of fuel. So that was one success that we got. As I said, we cannot achieve both the things. The emissions. Let us look at the emissions part. So for the emissions, yeah, you can see the energy consumption was more, but the emission part was here. So this is quite troublesome, right? The overall emissions was here 2.5706, but here the, oh sorry, so here, yeah, so here it was little bit higher for the MECMs, NEDC, but for the same NEDC in equivalent, normal equivalent consumption minimization, it was lesser. So why did that happen? Because you can see that most of the emissions, because of these things, we rapidly used in the non-zero emission zones. We aggressively use the engine so that we can save the electric energy, and then we kind of wrap up, and so because of that the emission actually got pushed to the non-emission zones, but we could ensure that there's zero emission zones, sorry, we push to the non-zero emission zones, but you can see that in the zero emission zones we could maintain zero emissions. So that was what was the thing, but it got spread into some other places. So that was the compromise which we had to make. But then it was just a little bit different. It was just 0.01 gram difference for that entire drive cycle. Similarly, this was 2.566, but here the modified emissions. This is how I'm talking about the entire drive cycle. Okay. But here, this is the unburnt hydrocarbon. But you can see the carbon monoxide. The carbon monoxide here was more in the ECMS, but here it was less. So because they go to different operating points, so it's very difficult to say whether, because it might so have in the hydrocarbon emission for some operating point is more, but for the same operating point the carbon dioxide may be less. Okay, so that is the reason why we got this kind of results. But then yes, we could have emissions. Obviously there were substantial emissions on the outside of the region, but not inside the region. So that was what was important here. Okay, so similarly, yeah, so similarly this is about the del SOC, the change in SOC for modified ECMS. Right? You can see the change in SOC. So there was the difference in the fuel consumption. So what was the different fuel consumption? So all these results are also presented. Okay. Yeah, so all these plenty of analysis were done. Energy consumption, integrated emissions, total integrated throughout the drive cycle, how much the emissions were given. And then, mind you, this is not just about the emission, it is also about the temperature. We saw that very interesting thing that at lower temperatures, the emissions, the fuel consumptions increased for the same drive cycle, to negotiate the same drive cycle, but the emissions obviously because of the fuel consumption, the emissions also increased at lower temperatures. So this is what we felt also like of pointing this out. Okay, so these are some of the concluding lines. We could there was a conventional energy management strategies which they have no predictive control. They have control, but they have no predictive strategy. So we modified that ECMS strategy, and then from that we could negotiate a zero emission zone thing. Okay, so the extension will work on future can be predicted based on. So we have not incorporated the traffic and uncertainty in the speed. We assume that the speed is known beforehand. Right? The speed it may not be that. Right? I don't think I have time for the third one. So maybe I'll take up some questions if anybody has anything. That's it for now. So I'd like to conclude by thank you for patiently listening.
Okay. Participants, do you have any questions? You can directly unmute and ask your questions.
Will you please highlight any research areas to work in this topic? Yeah, I think I have mentioned. So as I told that, so talking about hybrid vehicles, energy